So today we're going to start laying the foundation for our assessment, our learning, our analysis of the insides of the black boxes of machine learning algorithms. So the framework we're going to use is called statistical learning theory, and it'll slightly generalize the presentation from last week, as we'll see in a bit. So first we'll talk about what's called decision theory, which is kind of maybe even a broader subject than machine learning. We'll give a little high-level view. So it actually captured a lot of the problems in machine learning nicely. So in machine learning, or in data science problems in general, we're trying to usually make a decision, in a business setting, say, maybe take some action, maybe produce some output. Producing an output was kind of what we were talking about last week. And crucially, we'll need a way to evaluate our output or our action or what we produce, preferably in some automated way, preferably some numerical way. Okay. The generic term we'll use for what we produce is an action. And so examples of actions, if this were like classification, it could be 0, 1. That would be an action. Producing an output, a prediction, that could be the action. It could be in like traditional statistics. It could be deciding to reject the null hypothesis or not reject. In automated driving, an action could be, pressing the accelerator, steering the steering wheel. These could be actions produced by the system. It could be something that's kind of got complicated structure. So if we're doing machine translation, the input could be an entire paragraph of text in French, and the output could be the corresponding translation in English. Okay, that would be the action that we take, producing that translation. Okay, so here's a question. So what could be the action for predicting the position of a storm a few hours in the future? What would you want to produce?
Some sort of lat long.
Like a lat long. So your action would be to produce a lat long where you predict the storm will be. Okay. What else could you produce?
Its speed, data rate.
So, okay, so the type of storm, yeah, so its intensity, that would be like another description of the storm. But still on the location of the storm. So I have a concern. If you're just producing a lat long, okay, some kind of a radius, maybe some kind of expression of uncertainty, right?
Probability distribution.
Okay, like a probability distribution would be a very generic way to represent your uncertainty about where it's going to go next. That's nice. Okay, so that could be the action. The action could be to produce a single lat long. It could be to produce like a lat long in a radius. It could be to produce a full probability density on the Earth. All these things are possible actions that you could take for this problem of predicting where the storm will be. All right, good. So we have the action, and then the other piece that's essentially required for any decision theory is to evaluate the action in some way. So reason being that the goal of decision theory is really to find the optimal action. So to define optimal even, we need to have a way to evaluate how good an action was. So for instance, if we're doing the machine translation, how do you evaluate performance? Like, do you go word by word? It's a challenging problem sometimes, evaluation, but it's kind of a crucial step. So a lot of the challenge, kind of as we discussed last week, a lot of the challenge in formalizing a business problem is to figure out a nice way to evaluate the action. Okay. All right. So first two steps when you want to formalize a business problem is what's the action space, what's the action you're trying to produce, and how are you going to evaluate that action? And as you understand the problem better, you may evolve that formalization, just like we did in our case study of churn prediction. Right? The more we thought about it, we adjusted the formalization a bit. Okay. So we have the action we take, and then we have the need to evaluate it. We have the evaluation criteria. And then there's usually an extra piece, which is the input, right? An input to the system. Not always, but typically there's also an input to the system. So that could be the picture we get when we want to say is there a cat or not, or the storm's historical location, if we want to predict the future location. That would be input. And then finally, there is most typically an outcome or an output or a label, which is essentially the right answer. It's what actually happens. So where the storm actually ended up, or well, in the self-driving car case, though, there's not really it's not like the outcome is really a right or wrong answer, right? It's just you had an action that you wanted to take. You depress the accelerator, you steer the steering wheel, and the outcome is what happened to the car, where it ended up, how it moved, the position of the car in the world. So that's kind of the outcome. This is kind of a very general setting. So the typical sequence of events then is you observe an input X, you some way or another decide on an action to take A, you observe some outcome Y in the world, and then you evaluate how you did. You evaluate the action you took in relation to the outcome Y. So that's captured in the loss function L of it takes an action and the outcome, and it produces a number. So bigger number bad, smaller number good. So typically we want to assume that the outcome is independent of the action, the prediction, the action that we took. But of course, this is not always the case. So when would this be the case, and when wouldn't this be the case?
The outcome is just some variable you're trying to predict. Like, so our action is just trying to predict it. It's not going to influence the value. But so, for example, if you're looking at the census data and trying to use some information to predict some other information, but the outcome would change if it's like a car where the action is actually going to move the car.
Great. So for like the self-driving car case, the action you take affects the car. So of course, almost the whole intent is to influence the outcome of where the car goes. So the action and the outcome are highly dependent. But if you're trying to predict, are you saying trends in demographic information or something? And suppose you do it and you just don't tell anybody. Sometimes you make a prediction that could affect the world, right? If you're tracking a stock, for instance, and someone forecasts like, oh, I think the stock's going to go up. Yeah, it could affect the value of the stock. So even in that case, it's not independent. But if you kind of make your prediction, you keep it to yourself, and you don't act on it, then yeah, you could say that they're independent. All right. So we formalize these notions of actions and outputs or outcomes and inputs with spaces. So we have the input space, which we'll write X, action space A, and output space or outcome space Y. We'll be seeing a lot of these. All right, so just quick concept check in to see how much machine learning you guys have already seen. What would the spaces be for linear regression? Input, output, and action. So?
D-dimensional space for the...
OK, so linear regression could take a vector, say d-dimensional input vector. Yeah. Output?
It's a function space or taking input, output?
Linear regression. So the input, you get an input X, and then you produce an action, A. So what's being produced in linear regression by your prediction function?
Coefficients. A function. Coefficients.
All very interesting. OK. So this is perhaps a bit ambiguous. So linear regression is a learning algorithm. So the learning algorithm may take some training data and produce a function that's true. OK. So I guess what I should have said is, what are the spaces for the prediction function or decision function produced by linear regression? So that would take as input an RD vector. And what would this decision function or prediction function produce?
Numbers or real
real number, yeah. So the action space is reals. And then what's the output space or outcome space? This is kind of the true values you're trying to fit for linear regression. Also reals, yeah, also reals. OK. So the prediction function from linear regression takes RD as input. That's input space is RD. It produces a real, so the action space is a real. And what you're comparing your prediction to, the outcome space, is also a real. All right. How about logistic regression? You guys seen logistic regression? Some. All right, so input space? RD. OK. Outcome space? What you're trying to learn from? The outcome space is 0 and 1, typically. So your training data consists of pairs of inputs and outputs. And the input would be in RD, and the output would be a 0, 1, a classification. OK. But the action space, what your prediction function produces, what would that be?
So between 0 and 1.
Yeah, for logistic regression, usually you produce a number between 0 and 1, so that's like a probability. That's right. OK. So the action space you could think of as numbers between 0 and 1. You could think of it as the probability of 1. Okay. But as a set of, as a space, you could say numbers between 0 and 1. Yeah?
No, I was about to say, so the output of the logistic regression is actually a probability, right? It's not. I mean, it's
so
the likelihood between.
you'd like to interpret the out. So we know for sure that the output of logistic regression is a number between 0 and 1, and you'd like to interpret it as a probability. And that's, we'll see later in the course that that's a reasonable interpretation. Yeah. OK. How about support vector machines? Have you guys seen this before? Some, yes. Input? RD. OK. Output? Class label. Right. So 0 or 1, negative 1, 1. And action space. What do you produce? It's OK. We'll come to this. I just was curious what you guys have already seen before. All right. So support vector machine produces a number, a score. And usually, if it's greater than 0, you say it's class 1. If it's less than 0, you say it's class negative 1, the other class. So we have our input space, our outcome space, and our action space. The decision function takes an input and produces an action. That's the bottom line that we're trying to come up with. This is what we also were calling prediction function last week. That's what we're trying to come up with in machine learning. And the loss function takes an action, what was produced by our decision function, and takes the outcome that actually happened, and we give it a score. How good was that? How good was our action in light of the outcome that actually happened? So in regression, you might say, the action's a number, the outcome's a number. How close are they in square difference, for example? So formalizing a problem, we have the action space and the evaluation criterion. And then if a business person comes to you and a stakeholder says, I have this data science problem. If you're lucky, they'll have an idea of what they want you to produce. They'll want you to make a prediction function or decision function that produces some type of action, and they should know what type of action that is, like a number, or they'll want you to produce a decision on buy or sell, or these sorts of things. They should have an idea of the action space. But often they only have a rough idea of how they want you to evaluate it. So that's something you often have to use your own sense as a data scientist to come up with good evaluation criterion. But the bottom line is that they want you to produce that decision function that they can then deploy with their engineering team, make a rock solid decision function that actually works in the wild. All right. So we have decision function, and we use a loss function to evaluate its performance on a single input-output action combination. So how do you want to evaluate the decision function as a whole? If the stakeholder needs to know whether or not to deploy this decision function, they need to have a score, an assessment of how well it's going to perform. So the standard framework called statistical learning theory gives us a recipe for that. And it's essentially, it's kind of like the average performance that your decision function will get. But now that's what we talked about last week, kind of the average performance on a test set. But now we're going to formalize that a little more. So in statistical learning theory, we're going to make that assumption that we mentioned earlier, that when you take an action, it doesn't affect the outcome of the world. And we're going to assume that all the data we get, kind of these input-output pairs, the things that we use for training data, and the things that we're going to be working with in the wild are generated from some probability distribution, some joint distribution on the input space and the output space. And we're going to assume that all the data we get in pairs, these things that we're going to use for training data, XY pairs, are generated IID from this distribution. IID means independent. Each example is independent and identically distributed, so they have the same distribution. So essentially, in terms of last time, we're saying things like there's no covariate shift in the data, there's no concept drift, things are the same, and things are the same no matter when we get our data example. Okay, so we want our decision function, say fx, to do well on average. And what we mean by that is that the loss function evaluating f of x would be the action we take for an input x, for the corresponding outcome y is small in some sense. All right. How are we going to formalize this? We come to the first key definition of statistical learning theory. It's the notion of a risk. We call it a risk. Risk is really just a fancy name for the expected loss. So what does that mean? We have, someone gives us a decision function f. The decision function, remember, is what takes the input and produces the action. And we know how to evaluate its performance once we get the true output. So that's the loss of f of x. F of x is the action produced by the decision function, and y is the outcome. So the loss of f of xy is how well we did on one example. And what we wanted to define as the quality of a decision function's performance is the expected loss on a randomly chosen output pair from the distribution. So the risk of a decision function is defined as the expected loss on a randomly chosen example. So this is a nice idea because it gives a definitive indication of how this is going to do on average when you deploy it into the wild. The issue is that you don't really know this distribution that the xy's are coming from exactly. If you did, you could compute an expectation using some math or some simulation, but you don't actually know the distribution these xy's are coming from. So that's an issue that we're going to come back to. All right, but for now, this is kind of our gold standard evaluation. So hand in hand with this risk is the notion of the Bayes decision function, which is the decision function that minimizes that risk. So it's the best possible decision function when evaluated in terms of expected loss on a randomly chosen data point. All right. So we write this Bayes decision function as f star. It's the Fermi notation argmin. Yeah, OK. So argmin over f. This says look over all possible functions f, all possible decision functions f. See which one minimizes r of f. R of f is the risk of f, which is the expected loss of the decision function f. And argmin says find the one that's the minimum, and let's call that f star. All right. OK. So here you could think of the minimum as being taken over all possible functions. All right. So the risk of the Bayes decision function, remember the risk is the expected loss, is called the Bayes risk. There's some terminology that comes up. And also the Bayes decision function is sometimes called the target function. Target function because this is the best decision function that we could possibly hope to come up with. All right, so let's make this a little bit concrete. So least squares regression. This is kind of going to be our go-to simplest problem, the whole first part of this course. So say one-dimensional output space, of course, reals. We're producing reals. And the loss function we'll use is square loss. And so the risk of a prediction function is the expected value of f of x, that's a prediction corresponding to x, minus y, the actual value, square. Okay. Okay. We'll be able to show, in the homework, there's a small problem where we can derive the Bayes decision function. That's the Bayes optimal prediction for this score error risk. And it's going to turn out to be the conditional expectation of y given x. This is a very intuitive type of thing. This says, given the input x, y, of course, can have a distribution given the input x. The best thing to predict, because you have to predict one number that minimizes this expected square error, the best thing to predict is the expectation of that conditional distribution of y given x. And this is a simple calculation you can do in the lab. All right. So for square loss, the Bayes prediction function is conditional expectation of y given x. All right. Second example, multiclass classification. So let's define a 0, 1 loss. So k classes, if we predict, we're going to take an action space which are the numbers 0 to k minus 1, the k classes. And the output space will also be the same. And we'll get a loss of 0 if we output the correct class, and a loss of 1 if we have the incorrect class. All right? This is the 0, 1 loss function. And then, of course, the expected loss, or the risk of a prediction function, we'll just look at when does our prediction f of x not equal to the correct output y. Now, I've written this little boldface 1 in front. This is a notation we'll use a lot in this class. This is called an indicator function. So when it says 1 in the parentheses, it's itself a function that evaluates to 1 if the thing inside the parentheses is true and 0 otherwise. Okay. So you can evaluate this expected value of the loss function. And let's just work this through as a warm-up. So how do we compute this expected value? There's two possibilities, right? One is f of x is equal to y, and the other is f of x is not equal to y. Okay. So if f of x is not equal to y, what's our loss? 1. And f of x is equal to y, our loss is 0. So we can expand this out into 0 loss times the probability that the prediction is equal to the output, plus 1 loss times the probability that's not equal to the output. So that would be the expected loss, the expected error of our prediction function f. All right. So this reduces to, of course, just the risk of our decision function is the probability of an error. And so what's the Bayes prediction function? What's the best possible prediction function we can get for this loss and this risk? Well, maybe there's an error. What's the correct answer? What would be the right, for a given input x, what would be the right thing to predict for y?
The one which will minimize the probability of error.
One that minimizes the probability of error or maximizes the probability of being correct. So this is the probability that if k is the prediction, y is the correct output, then we're going to find the k, the predicted class, that has the maximum probability. Yeah. Okay. Very intuitive, obviously. Predict the class that has the highest probability. Yeah.
I'm kind of confused where probability comes up, because you define the target function as a function that minimizes the risk of all functions taking x to a. If a is equal to y, there's got to be one function that brings an x to the correct a. So shouldn't the target function, or shouldn't the minimal risk be 0? Or like, is it most likely, or is it actually 100%?
So this is a great question. So, so this kind of gets into what happens if a given input x, let's make it concrete. Let's suppose the input is 5. Inputs are numbers, 5. And the corresponding output, conditioned on the input 5, has a distribution in general. Let's suppose the distribution is 50% of the time it's 1, and 50% of the time it's we're doing classification. So it's 50% of the time it's 1, and 50% of the time it's 0. All right. So the Bayes decision function is only allowed to choose one thing to predict for any input. It's a function. A function can only produce one thing for any input. So if half the time the class is 0 and half the time the class is 1, and maybe there's a class 2, so you would never predict class 2, but the Bayes decision function has to choose one of those two classes. You see what I mean?
Could you repeat that once more? Because
Yeah, sure.
you mentioned that A is equal to Y in the first point, so all the classes are covered, right? There,
Yeah,
if there's a
absolutely.
class 2, then 2 can be predicted.
Sure. Okay. All right. So suppose the distribution that we're talking about looks like this. Okay, so for a particular input x, suppose 1, let's suppose there's 3 classes for simplicity, 0, 1, and 2. And then we have different values of x that we're not going to be concerned about. Okay, so suppose for an input 1, the probability of the output y being 0 is a half. And output 1 being also a half, and output 2 being 0. All right.
So is this going back on the point that there's just not enough information in X?
Yeah, there's just not enough information about in x to figure out what y will be definitively. There's some randomness still in the value of y given x. And so the best we can do in this case, well, you could pick either 0 or 1 to predict. Either way, we're going to get an error half the time. Sure. Good question. All right. So we've looked at some loss functions, and we've looked at some risks, and we've come up with some Bayes decision functions. And all of this is kind of abstract. There's no training data yet, right? We just talked about these expectations and minimizing expected losses. And the issue is that what I wrote down over here, the probability of y given x, we never really know that in real life. No one tells us that probability distribution describing the real world. So somehow we have to work around the fact that we don't know that distribution. We don't know px cross y. So, but the one thing that we can always do in machine learning or data sciences statistics is assume that we have some data, right? And that's what we're going to use. So we assume we have sample data drawn from this distribution, pxy, coming in pairs, x1, y1, to xn, yn, say, draw an IID from this distribution. And somehow we're going to use that to get around the fact that we don't actually know the data generating distribution. So why do we think we have a chance from a sample? I mean, there's, for instance, the strong law of large numbers. What does the strong law of large numbers tell us? If we have a bunch of random variables, sampled IID from some distribution, and we take their average, it converges to the expected value of the distribution, expected value of that variable. So this gives us some hope that with enough data, if we kind of put them together, we can converge to some property of the distribution as a whole. We can apply that to our risk. So introduce this notion called the empirical risk functional. So remember, the risk was the expected loss. The empirical risk is an approximation of the risk. So the empirical risk of a decision function f for the data set dn is the average loss on this sample of data xi, yi. All right. So although we had the expected loss that we really want, we don't know how to compute that expectation. So we compute the average loss on a sample of data drawn from the same distribution. Now, what would the law of large numbers tell us here?
Converges to the mean as n tends to infinity.
Yeah. So we want to say that this, in the limit as n goes to infinity, that this converges to the expected value of this thing we're taking the average of. So here, this was the law of large numbers, this average of the zi's. So what corresponds to the zi's here?
F of xi and yi, the pair.
The loss function?
It's the full expression inside the sum. The loss of f of xi, yi. What kind of object is that loss? What does it evaluate to? a number. It values to a number, just like the z's. So this is an average of a bunch of numbers. Are they, if we consider the training set random, then this number, this loss, we also consider random because it's a function of some random pair xi, yi. So we have this average of random numbers, these losses. Is it clear why the losses are random? Yeah, it's random because the data point it's being computed on is random. So, okay. So we have these average losses on sample data. And so the strong law of large numbers will tell us that this empirical average converges to the actual risk of the function. So this justifies one of the things we were talking about last week. We talked about validation set and test set. Remember, the test set was to take a decision function and get an estimate for how well this will work on new data. So this is our justification for the test set. We've chosen a function f without looking at the test set, right? And we have this brand new set of data, sampled IID from some distribution. And the average loss on that data is going to be a good estimate for the expected loss on new data. So as far as using test set for evaluating performance, that's justified by the law of large numbers. Okay. So we want to get the risk minimizer. We don't have access to that. So we could use the empirical risk minimizer instead. Is that good enough? So in other words, this evaluates the performance of f. That's great for a test set. But what about, before we get to the test set, what about when we're still trying to find f? Can we use this empirical risk to search for the f that's the best in terms of empirical risk? Or is that risky, so to speak? OK. All right. So first, let's define. F hat is an empirical risk minimizer if it minimizes the empirical risk. The hat is used when we want to say that the function depends on some data. Okay. So f hat depends on the data. Why? Because the data shows up in the empirical risk. All right. So do you guys think this is going to work or not going to work? Empirical risk minimization. Find the function over all possible functions that minimizes this empirical risk, the average risk on some data. Think it'll work if we have enough data? Maybe.
So wait, are we saying that we are minimizing it for all the data set and then testing it on that again? Is that
okay? Good question. No, so Rn hat depends on some training data set, some sample, and we're searching over all possible functions for what has the best performance on that sample.
So that again, this comes back to we are trying to make our decision based on minimizing the error on the training data, but we should ideally do it on a validation set instead.
Okay, so you're saying that essentially we could find an f that does really well on R hat and f, which is the empirical risk, so the average performance on some data set, say the training set. But you're saying this may not have good performance on new data. In other words, in our new terminology, what you're saying is this may not have good, it may not have good risk. It may not have good expected loss. So it may not have good performance on a new randomly chosen data. So f hat may perform very well with respect to R hat and this empirical risk, but R of f hat may be poor. R of f hat, the risk of f hat, the expected loss on a new data.
So in other words, this minimization. So wait, is it because when we're doing this, we are violating one of the assumptions we made in the law of large numbers or something? And so
no, good question. All right, let's come back to that. All right, let's get a concrete example where this can go totally awry. Very simple example, but it'll also help us rehearse some of these spaces. So here's our very simple problem. We have an input space x. It's the numbers 0 to 1. The output space is y, also the numbers 0 to 1. We're going to assume we know the distribution of our data. So the input space has uniform distribution on 0, 1. So it's equally weighted across all these possible input values x. And the output is always 1. All right? So input's random between 0 and 1. Output's always 1. That's the true distribution. We get a small data set from this true distribution, 3 points. Of course, they're all 1, has to be. And some nicely, conveniently located x's. Very lucky. OK, so we want to find an empirical risk minimizer of this. We could say 0, 1 loss. We could use square loss. It doesn't matter. Here's an example. Here's a function that is always 0, except exactly at the 3 data points that we observe, and otherwise 0. OK. So what's the empirical risk? What's the average loss on the data points for this prediction function? 0. Whether we're using square loss or 0, 1 loss, it's 0. OK. What's the risk? What's the actual expected loss for a randomly chosen data point from this distribution? Remember, the distribution is uniform on 0, 1, and y is always 1. It's 1, because with probability 1, we're not going to hit one of these 3 points. We're going to hit somewhere else. Anywhere else, we're predicting 0, which is wrong. The correct answer is 1. So the average, so the loss at every point, almost every point, is going to be 1. And so the average of these 1s is 1. So yes, risk is 1. The expected loss is 1. Questions on that? All right.
So it means there are multiple empirical minimizers that satisfy this situation. One of it will match the risk factor, the true risk. The other will not. Right?
Yeah. So the comment is that there are many possible empirical risk minimizers in this situation, and visually we know the answer that one of them works quite well, but some other ones, like the one we found, does not. Right. So maybe ERM can be good sometimes if you choose the right one. Is your comment? Yeah.
Would it always be the case that for the true sort of real minimization function, there's only one?
So the Bayes optimal, is there always a unique Bayes decision function? No. We actually, the example over here was one example. Because given a 1, we could predict a 0 or a 1, and it has the same performance. So no, not necessarily unique. Any other questions or comments? So what's happening here? What's the principle here? This is just a lot of infrastructure, a lot of math to say exactly what we talked about last week.
It's hard to find the right function to use as an estimator.
Yeah, so what happened here in our terminology of last week?
We overfit.
Yeah, overfitting. We're overfitting the data, exactly. Simple as that.
Yeah, we need to generalize it more because we are not generalizing over here.
Right. So there's this notion of generalization, which is how well are you going to perform on new data based on the training data that you've seen. OK. So as we've kind of said, as Joy just said, so empirical risk minimization approach here, yeah, it fit the data, but it just fit the data. It essentially, in the example we gave, it memorized the data, but was completely wrong on new data. And what we want to do is we want to somehow find a better way to spread information about the training points we've seen to other training points, maybe nearby training points. And really, this is like the essence of machine learning, which is how do you generalize from the specific examples you've seen to other parts of the input space you haven't seen. And there are better and worse ways to do that. So intuitively and in practice what works is you want to have some kind of a, for instance, smoothness to the prediction functions. You expect that in most situations, in many situations, if you have this kind of input domain, this continuous input domain, that points that are very, very close to training examples, probably all else equal, should have similar, will have similar outputs. So maybe it's a better idea that instead of predicting 0 right next to something that a training example had 1, you do something, you change it more slowly. You want to put it closer to the output. And so a lot of the strategy of machine learning is finding ways to constrain the functions that you're predicting to have this kind of, some kind of a smoothness or some kind of a property that tends to spread information from one part of the input space to nearby or other parts of input space. So it's like this spreading of information from the training set to the full input space in some way that makes sense, that generalizes. All right. So one approach, which we're going to talk about a lot, is called constrained empirical risk minimization. So the idea here is if you have some notion in your mind about what types of functions make sense, what types of functions kind of have the right smoothness or consistency or whatever it is that you think the right prediction function has, then just constrain to that set of functions, all of which have the property you think will work, instead of considering all possible functions. So in other words, if you came to this problem, you would say, you could say a priori maybe that any function that looks like this is silly. You would want a function that changes more slowly. And so you would, in a constrained ERM setting, you just say, I will only consider functions that, for instance, change slowly as we vary x. All right. So the name for this constrained set of functions that we consider is called a hypothesis space. And when we apply it, what we'll do is we'll find the minimizer of the empirical risk within that constraint set, within that set of functions that we think a priori have a chance of doing well. So formally, hypothesis space, we're going to be denoting it by f, this script f for space of functions. And it consists of functions mapping, as always, as decision functions do, from input to an action space. And it's the collection of decision functions that we are considering. OK. All right. So besides having the regularity or the smoothness that we think the right function should have, we also want one that's easy to work with, that we can, as we'll see later today, do minimization problems with and actually find the empirical risk minimizer. You know, just because we define a hypothesis space that has all the right functions, we have to actually solve the problem of finding the empirical risk minimizer in that space. So we need to choose a space that's easy to work with. So we'll see examples soon. All right. So just what are some hypothesis spaces you guys have seen already? Say again?
Functions in L2. So
let's give me input space, output space, and describe the function.
All set of all continuous functions from RD to R.
Great. So input space RD, action space R, so it's a regression setting, and the set of all continuous functions. That is a hypothesis space. You said it, continuous, right? Great. OK, another example.
Polynomial of order less than n.
Great. Polynomials of order less than n. We talked about that last week. Mapping from R to R, RD to R. Great. What else? Have you guys seen other things?
Differentiable and continuous functions.
OK, so we're adding some more technical conditions on the functions, differentiability. These
so as in they're smooth.
More smooth, perhaps. Great. OK. All right. All right, we'll see a lot more types of hypothesis spaces. So constrained empirical risk minimization. Argmin, instead of just over f, like all functions, now we say argument of f in the hypothesis space f of this empirical risk. All right? That's the empirical risk minimizer that we're going to be talking about, ERM. We'll denote it f hat sub n to indicate it's based on a data set of size n and training examples. Okay. So there's one other thing we're going to define before we take a short break, which is in the class. It's like the Bayes decision function, but the Bayes decision function has the minimum risk, the minimum expected loss over all possible functions. Let's also define the minimizer of expected loss constrained to the hypothesis space F. Okay? So it's the best we can do under the constraint of the hypothesis space. Now, can we ever find this function? Not really, because we don't know the probability distribution, so we don't know this expectation. So this is still, just like the Bayes decision function, this is still kind of an aspirational function we wish we could get that we don't really know how to calculate, but it's very useful to keep in mind as kind of our target, as our goal. Okay, any questions before we take a break? Yeah.
How do you define the hypothesis space? Is it based on the input data set, or like how do you
come up with the hypothesis space? Well, that's basically the whole problem of this class. That's exactly the inside the black box problem. So if we do outside the black box machine learning, we don't have any idea yet what the right hypothesis space is. A hypothesis space goes hand in hand with a learning algorithm, typically. So it's just like choosing your learning algorithm, choosing your hypothesis space requires understanding something about your problem and understanding how the hypothesis space will perform. So that's kind of one of the basic questions of the class. Yeah.
Is decision function same as a prediction function?
Yeah, decision function is, we're using that interchangeably as with prediction function here. Decision function can apply more generically. That's the term people use in decision theory.